Okay, so we are now in a position to start talking about linear modeling. What we have done so far is that we know how to do single sample, two sample, and pair t-tests. And we also have in mind now what type 1 and type 2 error is and what statistical power is. We also learned about type M and type S error. So all this is the background that we need in order to start building up to the linear model. So as you will see, the t-test and the linear model are related and they have a very close connection. So to start with, I want to use a very famous data set. This is a paper that was published in 2005 by Grodner and Gibson on subject and object relative clauses. So what we have here is 42 subjects have been exposed to subject relatives or object relatives, and we are looking at the reading time in each of those two conditions at the verb inside the relative clause, right? So basically what we have is a relative clause where there's a verb inside the relative clause, and the position of this verb in subject and object relatives will be different. So let me see if I can just quickly tell you what the scientific context of this is. So we can have sentences like, right, let's take this one. Let's start here. The man who saw the woman, let's say we can have another verb like left here. Okay, so what we have here is a subject relative. This is a relative clause, and inside this relative clause there is a verb, and this is called a subject relative because the head noun man is actually the subject of the verb, right? So contrast this with the man who the woman saw left. All right, so now what we have is, again, we have a relative clause and we've got a verb inside the relative clause, just like in the subject relative, but this time the head noun man is actually the object of the relative clause. So one of the research questions that the Grodner and Gibson study had was, is there a difference in reading time here versus here? Okay, so there's obviously a problem in this research question because the word position of the verb saw is not identical in these two relative clauses. So it's kind of a confounded design, but we're going to ignore that detail right now and just think about the fact that we have object and subject relative clauses, which in this data set are called subject relatives are called subject gaps and object relatives are called object gaps. And what we have is reading times in milliseconds at that relative clause verb in the two kinds of conditions. And you can see here that we have repeated measurements from some different subjects because each subject is seeing multiple versions of each type of relative clause. All right. So the first thing we can do here is that we can calculate the average reading time in the subject and object relative clauses. And so what I've done here is exactly this. I have the mean for object relatives 471 and the mean for subject relatives. The order in which these two means are displayed here is alphabetical, right? So O comes before S in the alphabet. That's why object gaps are shown first. Okay, that's the only reason here. And I will elaborate on this point later. Okay, so but what we do observe here is that object gaps have a longer reading time in this data set than subject gaps. So basically what's going to happen is that we're going to assume that the object gaps have some reading time mu sub 0, some true reading time mu sub 0, and subject gaps have some true unknown reading time mu sub s, and the null hypothesis will be that we want to know whether the difference between the two means is 0 or not, right? It's the standard pairwise test that we would want to do. So the correct t-test that we would do in this case, right, would be first we would do a by subject t-test and then a by items t-test, just like I had shown you in the previous lecture. So the correct way to do this is to first create a by subjects data frame by aggregating the reading time by subject and condition. That means averaging over the items. That's what I've done here. And you can do the same thing by items as well. You aggregate by items and conditions such that the averaging is done over the subjects. That's the second line here. And so you can do the by subject t-test by carrying out this command here that I've shown. So I've explained all this before, so I won't walk you through this again. But what we learned from doing this t-test is that there is a significant difference between the object and subject relatives, right? We see that here. In the by item analysis, we also see a significant difference, right? So we would conclude from this these t-tests that we have a significant difference between the two conditions. Okay. All right. Now let's just think about the by subject analyses for a moment. Okay. So we're just going to focus our mind on this data. So we're going to forget about the by items analysis for a few minutes. So if we just focus on the by subject data and calculate the object gap and subject gap means, we see the same means that we saw earlier, right? So they're just averages of averages, so it's not going to be any different. But what's interesting is that now we can talk about the object gap or object relative data as coming from a normal distribution with a certain mean and standard deviation. So what would be the mean for the object gaps? Well, that was the mean that we calculated from the data. So we take the sample mean as our best guess about the true mean that might be generating the object relative data, and there is some standard deviation associated with that, right? So what we are saying is that we are assuming that the object relative clause data, right, which I write like this, is a random variable which is assumed to have associated with it some underlying PDF. And what is that underlying PDF? It's the normal distribution. I'm just assuming a normal distribution. I could have assumed something else with this sample mean and some estimated standard deviation. That's why I'm writing sigma hat there. Okay, so that's what I've written here. You can do the same thing with subject relatives, right? So what you can do is you can say that, okay, look, the subject relatives have a sample mean of 369. But 369 can be written in terms of the object relative gap and the difference between those two, right? So the difference is 102 milliseconds. I hope that this calculation is correct, but instead of writing 369, I could write this here, right? So I'm just saying here that my subject relative is assumed to be generated from a normal distribution with mean equal to, I'm using the object relative gap mean as my reference point and subtracting from that the difference between the two relative clause types, okay, which is 102 milliseconds. So the point here is I can write down an underlying model, an underlying generative process for the object and subject relatives in terms of two normal distributions with a certain mean and standard deviation. Okay, so this actually brings us to the linear model, because we can now talk about the object relative clause data's distribution as a sum of two terms. Okay, so how will we write this? We can write the object relative clause data's distribution as the sum of a fixed number 471, that's the mean, and some random variability around it, and that variability is characterized by the standard deviation sigma hat. Okay, so what I've done here is I've written instead of writing down this statement here, I've written an equivalent statement in a linear fashion, right? So I've written that my object relative clause data is actually got a fixed value, 471 is the mean, and there's some random variability around it, and that random variability is characterized by a normal distribution with mean 0 and some standard deviation which I'll estimate from the data sigma hat. Okay, similarly for the subject relative, I can also write this statement here. I can write this statement here equivalently in this linear modeling sort of framework, right? So now notice that I can actually figure out the standard deviation sigma hat because I already know the observed t-values from the t-test that I did. I know the difference in the sample means, and I know the sample size, right? So that's why I can do some simple algebra and work out my standard deviation, which is 213. So I just did all these calculations here. Basically all I'm doing here is that I have my observed t-value, and I've got my difference in means, which I've written here as x bar, but let me write it as d here. And I've got some unknown standard deviation divided by the square root of n, which is, I don't know, what was it, 42 subjects, so square root of 42, right? And so all I have to do now is replace dt with the observed t with the observed values, and I can figure out this s value here, just algebra. Okay, so basically what I've done here, what I've achieved here is that I've written the let me see here, right? Let me go here. So what I've done is, oops, sorry. What I've done here is I've written a model for how object relatives are going to be generated. So there will be some mean for object relatives, which I'll write as beta 0, and there will be some variability around that mean, which I'm going to define in terms of a random variable which I'll call epsilon, which is assumed to come from a normal distribution with mean 0 and some standard deviation sigma, which I'll estimate from the data, right? Similarly, for subject relatives, I'm going to write my model for subject relatives in terms of the fixed value that the mean of the object relative plus some adjustment, which I'll call beta 1, and again the same random variability that I mentioned earlier. So basically what I'm doing is I'm just rewriting the underlying generative process for the object and subject relative class data as linear models. Okay, so that's all that I've done. It's just a straightforward rewriting of my original statements about how I think the data were generated. Okay, all right. So this is my subject and object relative clause restatement of the model. This is what I just discussed. And so I can talk about the average reading times as estimated from the data in this sloppy manner. I'm not being very formal here, but all I'm saying is that the mean reading time for object relatives is this term here, and the mean reading time for subject relatives from the data, of course, right, is this term here. Now, what I want to show you now is that the LM function in R is actually going to provide you with this restatement of the underlying generative process, right? In other words, it's going to give you estimates of this term and this term as an output of the linear modeling function. Okay, so we can now make a little bit carry this logic slightly further by finding a uniform way to write down the two linear models for object and subject relatives, right? So what we can do is, so earlier what I had done was, let me show you. Earlier I had this beta 1 term in both the object, only in the subject relative case, but I could write the linear model for the object relative and for the subject relative in a completely uniform manner, okay, with this simple change. So I'm going to write beta 0 and beta 1 in both models, right, for object relatives and subject relatives. But what I'm going to do is that I'm going to multiply this beta 1 with 0, right, and multiply this beta 1 with 1. So the effect that this will have is that in the object relative, I come back to my original model, right, which I had shown you earlier, this one here, but because I'm multiplying beta 1 with 1 here, the model that I get is beta 0 plus beta 1 plus epsilon, as I had shown you earlier here. Okay, so basically what I've done is now I have just restated the model that I showed you earlier by adding this so-called contrast coding that ensures that I have a uniform way to talk about the object and subject relatives, and I can recode the two terms 471 and 102 by multiplying them with a 1 or with a 0. Okay, so I can make them appear and disappear. This is what contrast coding is going to achieve for us, and in fact in the LM function that we are about to use for fitting such models, what we're going to do is that there will be the column called condition in the by subject data, which has the words object gap and subject gap available in it, right? They will be numerically coded to 0 and 1 underlyingly inside the software in order to achieve this uniformity in presentation that I'm showing you here. These zeros and ones will be internally defined in the software, and you can see what the internal definition is by typing contrasts, the name of your aggregated data frame, and then the condition column, right? So it tells you what the recoding is internally, such that we can display the model estimates, you know, the 471 and 102. These can be displayed as the output of the linear model. Okay, so this is exactly what's happening here. I'm now fitting a linear model of raw reading time as a function of condition. Remember that we had done something like this with the t-test. I showed you the syntax earlier. With the t-test we could have written raw RT as a function of condition. This was one of the possible syntaxes that was available for the t-test. We're using the same syntax now in the linear model, and I'm using the aggregated data by subjects. Okay, so once I fit this model, I can look at the output of this model, the summary from this model, and in particular I'm looking at one subset of the output, which is called the coefficients. And the coefficients that you're seeing coming out of this model are the two numbers that we've been looking at earlier, right? So these two numbers here, this one here and this one here, right? So these are called the intercept and slope respectively. So this is called the slope of the model, and the reason it's called the slope is that really what we are doing is we're actually fitting a linear model that looks like this. This is something you must have encountered in school. If you're fitting a linear model like this, and if the x value here is 0, this is the intercept. This is called the intercept, and the slope of this line, which is the what is this, dy over dx, the difference here between this value and this value is called dy, and dx is the difference between this value and this value. So this ratio dy over dx actually gives you the slope of this line, right? So this is something we did study in school, but we forget all this, right? So that's why we call it the intercept and slope. And really this line can be described, if this is the y value and this is x, right? So we can describe this line as beta 0. So beta 0 is this intercept here, and the slope would be beta 1. So we could describe this line completely with these two numbers, beta 0 and beta 1, right? So basically that's what we are doing with the linear model. It's giving you these intercepts and slopes here, all right? So what the linear model is giving us here, given the contrast coding, is the mean reading time for the object relative clause from the data. That mean reading time is 471, and the difference between the subject and object relative clauses, which is 102 milliseconds in this data, right? So that's what the intercept and slope actually gives us, and this interpretation of the intercept and slope is a consequence of the way that we set up the contrast coding, the 0-1 coding for the slope, right? So now, as I showed you earlier, you can use the contrast function to figure out what the contrast coding is for your particular data set. And what I'm showing you here is that the you could have decided, so let me remind you earlier what we had. We had the object gap coded as 0 and the subject gap coded as 1. You can flip this ordering by changing what is coded as 0. Okay, so you can make the subject gap coded by 0, and you can do this by changing the level ordering in the factor coding of the condition column, right? In the by subjects aggregated data frame, there's a column called condition which has values like obj gap and subj gap. As I mentioned earlier, the alphabetically first word is obj gap, right? And so by default R treats that as the baseline, and that's why it codes it as 0. And that's why in this example that I was showing you here, for object gaps I code the slope as 0, right? Because it's alphabetically first, we treat that as the baseline. But you can decide to change that, and the code for doing that is shown here. You can change what is the first level of this factor, we call it, right? So the baseline level of the factor can be set as subject gaps, and once you do that and you look at the contrast coding there, you will see that the 0 coded element now is not the object gap but the subject gap. Okay, so this just shows you that you can decide which one is going to be coded as 0 or which one is going to be coded as 1. Now if we did recode the object and subject gap in this way, as I have just done here, with subject gaps as the baseline, what will change? What will change is that the intercept will now reflect the mean of the subject gap, right? And the slope will now reflect the additional cost of processing the object gap. That's why the sign has changed now, right? So it's very important to understand the meaning of the intercept and the slope as a function of how you coded numerically coded the factor levels of your predictor, in this case the relative clause type. Okay, all right, so so what I've done here is that I've gone back to the original coding. I've recoded the factor level so that object gap is the baseline again, so that we have the same setup as before. Now in mathematical form, this model now looks like this. The reading times that we have in our data are now assumed to come from some linear model, right, with some intercept and some slope associated with it, and the intercept and slope are the beta 0, beta 1 coefficients that I've been discussing so far. The meaning of the intercept and the slope are going to be the meanings will depend on how you do the contrast coding. Okay, but the interesting thing here is that we will always be interested in finding out whether we can reject the null hypothesis that the slope is 0, right? So a null hypothesis will always be, is the difference between the relative clauses 0 or not, right? That's what I've written down here. So that's where the hypothesis testing part comes in the t-test. Okay, so as I mentioned, the contrast coding actually determines the meaning of the beta parameters, and we are now using the object gap as the baseline, so it's coded as 0, the other conditions coded as 1. Okay, now just a notational detail here. I'm going to make a distinction between the true beta 0 and beta 1 parameters. These are the unknown values out there in nature which we are going to estimate from the data, right? So the estimated values from the data I'm going to write as beta 0 hat and beta 0 1 hat, but the underlying true values that we don't know are going to be called beta 0 and beta 1 respectively, right? So our estimate from the data of beta 0 is going to be called beta 0 hat, and that's 471 for object gaps. And the estimated mean subject relative clause processing time will be the sum of those two estimated beta parameters, which is 471 plus the number minus 102, so that's 369. Okay. Now, I had coded object gaps as 0 and subject gaps as 1, but I could have done something different. I could have coded object gaps as 1 and subject gaps as minus 1. So really what I'm doing when I do such a reparameterization is a reparameterization of the predictor. what I'm doing here is that I'm changing how I represent this linear model. So the linear model now will have either +1 here or -1 standing in for this condition variable, depending on whether it's an object relative or subject relative. What this will do is something very interesting. What this will do is that it will change the interpretation of the intercept and slope coefficients that we have been looking at right now. Okay, so what I just did here in this line here is that I'm using the if-else command to recode object gaps such that they're coded as a +1 and the other condition, which is subject gaps, coded as -1, and I've saved that as a vector called cond, okay, for condition. Okay, so now I can check what my relationship is between this new vector cond and condition by using the Xstamps function, and you can see that +1 is representing 42 rows in the data frame. This is the aggregated by subject data, so I have only one data point per condition for each subject. Okay, so I've got +1 representing the object gap and -1 representing the subject gap, right? So you can see that I have done the contrast coding correctly now. When I change the numerical codes for object and subject gap, I've done what I intended to do, namely coded object gaps as +1 and subject gaps as -1. I'm just doing a sanity check here. Okay, all right. So now I'm going to fit the linear model with this new contrast coding. Remember that cond is now labeled +1 or -1 depending on whether we have an object gap or a subject gap. Now if I look at the output of this model, and this is one way to extract the coefficients from the model. Okay, so when I look at the coefficients from the model, I get different numbers. I don't have the earlier numbers that I had seen. So I'm seeing a different number for the intercept from the slope now. What's going on? What's going on is that this 420 is now the grand mean. It's the grand average of all the data that I have, and condition, the 51 milliseconds value here, is the deviation from the grand mean of the object and subject relative clauses. Remember that object relatives are coded as +1. So for the average for the object relatives, so the object relative average will be the grand mean plus 51 milliseconds. And because subject relatives are coded as -1, the sample mean, the estimated mean for subject relatives will be the grand mean minus 51. Okay, so that's basically what the coding does. It changes the interpretation of the intercept and of the slope, right? Of course, why would we want to do this? I've not explained this right now. Just follow my story. All this will become clear once I discuss contrast coding. Okay, so what's happening with this reparameterization now is that the intercept estimate now represents the grand mean of the data, and the two relative clause processing time estimates are coming now from this summation. This is the object relative, this is the subject relative case, right? The end result is the same, right? No matter how I reparameterize this linear model, the estimate from the data for the object and subject relative is exactly what we found earlier. Nothing has changed there. All we have done is that we've changed the way that we represent the linear model that is assumed to generate the data with this +1 -1 coding. This +1 -1 coding is called sum contrasts. Oops, I lost my my pen has stopped working. So these are called sum contrasts. And the first 0-1 coding that I had shown you earlier, those are called treatment contrasts. Okay, so we are going to revisit the idea of the sum contrast and the treatment contrast later when we look more closely at contrast coding. But right now I just want you to be aware that the +1 -1 coding is called a sum contrast, and this is the contrast coding that I'm going to use in almost all the analyses that we will actually do. Okay, so this is your first contact. Maybe this is your first contact with the idea of a contrast coding, but all I'm doing is I'm representing the data. Each of the rows in my data frame, the by subject aggregate data, are assumed to be generated from a linear model with some intercept and slope and some residual variance, some variability, and the intercept and slope can have different interpretations depending on how you set up the contrast coding. Okay. All right, so let's stick with our sum contrast coding now, and we are going to, as I said, our null hypothesis was about the slope, and our null hypothesis was that the slope is going to be 0, right? That means the difference between the object and subject relatives is going to be assumed to be 0, right? So you can write the null hypothesis in this way that I've shown you here, right? Mu obj is the true reading time, unknown true reading time of the object relative, and mu subj is the unknown true reading time of the subject relative. That +1 -1 coding is showing up here as well in this hypothesis test, and so you can think of it. Think of the +1 -1 coding as actually representing the null hypothesis test's coefficients that I'm showing you in equation 9 here. Okay. I will make this a little bit more precise very soon, but what I'm trying to show you here is that there is a relationship between the +1 -1 coding and the hypothesis test that I'm actually carrying out when I do the linear modeling hypothesis test. Okay. All right, so now my model is for object relatives, it's this one here in equation 10, and for subject relatives, it's the model shown in equation 11. So we are now ready to think about the linear model in more formal terms now, right? So the linear model that we are now fitting is basically going to look like equation 12, and our goal is going to be, whenever we fit a linear model, will be to estimate these parameters beta 0, beta 1, and the sigma parameter, right? So mathematically the model will be written as shown in equation 12. And as you can see, one of the assumptions of this model is that the epsilons, the residuals of this model, the deviations around the fixed values beta 0 and beta 1 by condition, are going to be coming from a normal distribution with mean 0 and some standard deviation, right? So this assumption can be checked in the model. So when you fit the model M1, once you fit the model M1, you can extract the residuals from this model and look at this residual graphically, right? So if you plot the residuals and compare the residuals to a standard normal distribution, that's the x-axis here. You've got the standard normal distribution on the x-axis, and you have the residuals from the linear model on the y-axis. What you would expect is that if the residuals from the model are completely normally distributed, they should match up perfectly with the standard normal residuals. So what you should see, if you have a perfect match up with the standard normal distribution, that's what I was trying to write here, normal distribution with mean 0, standard deviation 1, and on the y-axis, if you have the residuals from the model, right, you should see a straight line like this, because they should match up, the quantiles should match up 1 to 1. My cat is trying to get into this room. So the quantiles should match up 1 to 1 if the residuals in the model are normally distributed, and you can see that that's not happening here, right? Because the diagonal is this one here. Here's the diagonal, and you can see that there's a huge skew in the data. So this assumption of the model is not being satisfied in this particular model. Okay. And you can also visualize this model by drawing a histogram of the residuals and overplotting the standard normal distribution on top of it. So I've got the standardized residuals with standard deviation 1 here. These are the histograms, and you can see that the model is not doing super well. The assumption is not really being met in this model, right? So we can improve the situation by log transforming the data, right? So what we can do is you take the raw reading times and you convert it to a log reading time, right? So basically what is going on here is that the reading times from the data are actually distributed with a skew like this, right? 0 is a lower bound on the reading time. You can't have less than 0 milliseconds reading time, right? And so the normal distribution has a different shape. The normal distribution assumes a completely symmetric distribution, and so the reality of the data is that it actually has a skew like this, right? This normality assumption is not very reasonable for reading times. Okay, so that's why it's often sensible to take a log transform on the reading times. And once you convert your reading times to logs and fit the linear model on the log reading times, what will happen is that your intercept and slope will now be represented on the log scale. It's not represented in millisecond scale but log milliseconds. Okay, so this creates some complications in interpretation, which I'll just discuss. All right, so now on the log millisecond scale, the grand mean with the sum contrast coding is 5.9488. That's correct, right? Yeah. And the deviation around the grand mean for object and subject relatives is 0.08 on the log millisecond scale, right? So I can compute the object and subject relative clause estimated log millisecond reading times, right, from this model. Nothing much has changed. I've just switched to the log scale here. Okay, so now my model is the dependent variable is log reading time, and the model itself is the same now. I've got beta 0, beta 1, and epsilons, right? So now I can check the residuals on the log model, and now you will see that we get that characteristic diagonal shape that I mentioned, right? So this is a much cleaner diagonal shape. So the match between the standard normal residuals the standard normal distribution and the residuals from the model are pretty well matched now. So you can see that we have a much more reasonable the model assumption is better met with the log transform data than with the untransformed data. Okay. All right. So, and if you look at the histogram of the residuals against the standard normal, you see that now you don't have that gap that we had seen earlier, right? If you remember this, there was no data here, right? So now we have a reasonable overlap with the standard normal distribution. So the model assumptions are better met with the log transform here. Okay. Why is it important for the model assumptions to be met? Well, the hypothesis testing procedure requires the residuals to be approximately normal. If they're not approximately normal, then the statistical test is not valid. That's the problem. Yeah. So my cat is back. I'm going to try to ignore her and see what happens. All right. So right. So we have these log transform data, and Molly. Yeah. Right. So we have these log transform data, and we have the estimated log millisecond reading time for object relatives and the estimated log millisecond reading time for subject relatives, right? So once we have fit this model on the log scale, if we want to get back the estimates on the millisecond scale for each of those two conditions, it's very easy to do this. It's easy because what we know is that if you have the log of some variable, I'll call it log of y, I can exponentiate the log to get back y. Okay, so that's a result you might have encountered earlier in life in school, but you might have forgotten. Okay, so I'm reminding you of this now. So basically, if my model is log RT and I've got beta 0 plus beta 1 as the the coefficients, I can transpose this, I can transform this back to the millisecond scale by exponentiating both sides. So let me do that. I'm going to exponentiate this side and I'm going to exponentiate this side, right? Once I do that, I get RTs on this side and I get the exponent of beta 0 plus beta 1 here. And now I'm basically ready to transform back my log RTs back to the millisecond scale, because all I have to do for object relatives is that I have to plug in the beta 0 hat estimate and the beta 1 hat estimate, sum them up and exponentiate. I will get the milliseconds values back, right, for object relatives. And for subject relatives, I would have to take the beta 0 hat minus the beta 1 hat and take the sum of the beta 0 hat minus beta 1 hat and exponentiate that and get back the estimate for the subject relatives on the millisecond scale. So that's a back transformation procedure, and that's what I've done here. And when I look at the two differences in reading times back transformed from the log RT model, what I find is that the difference between the two conditions is now 65 milliseconds, not 102 milliseconds that we saw on the raw scale when we fit the original model. Now, I'm skipping over some details here, but basically what's happening is that when you log transform the data, the extreme values are going to get compressed in the data. Okay, there were some extreme values in the data. They got compressed in the log scale. That's what the log does. You do your estimation in the compressed scale, and then when you transform back to the millisecond scale, you will get a smaller difference between the two condition means. Okay, so this is not the full story, but it's good enough for now, right? So you will certainly get different estimates from the model depending on whether you log transform or don't log transform the data. But because the normality assumption is not satisfied with the untransformed data, it is very important to think about how to meet that assumption, or approximately meet that assumption. And a log transform is often the right way to go with reading time data. It can sometimes happen that a different transform is needed. You can sometimes need a reciprocal transform. So for example, if your reading times are on milliseconds, you can transform the reading time to 1 over RT, right? So convert it to a speed of processing instead of processing time. So the reciprocal transform is also sometimes used to meet the normality assumption reading data, right? So these are different transforms that you can do. Right now we are only discussing the log transform, but the point I'm making here is that you should not be disturbed by the fact that the difference in the two means is different depending on how you do the transformation and back transform, right? The difference, this is arising from the way that the model is estimating the parameters and the scale in which it's estimating the parameters, right? And as I mentioned before, model assumptions matter in hypothesis testing. You can't just ignore the normality assumption. You will sometimes see people saying that the normality assumption is not so important. Don't listen to them. They don't know what they're talking about. Okay, so the normality assumption can never be perfectly met in the data, but one should make a good attempt to come close to meeting the model assumptions. Right? There are very serious adverse consequences to ignoring the model assumptions. Okay. All right. Okay. So the summary for everything that we've learned so far is we've understood how treatment contrasts work, roughly speaking, and we understood how some contrasts work, right? I gave you a first contact with contrast coding, and I also explained the sum contrast coding in some detail, and I mentioned that this is the coding that we will use in most of the work that we'll do later, right? I will give another lecture later on in this course on contrast coding. And as a preview to that lecture, there's a paper that we've written that you should read that spells out much of these details. But I will walk you through all the details later on, right? Okay. So now I want you to think about the fact that the Grodner and Gibson data, the relative clause data that we are looking at now, this is a repeated measures data set. Okay, so every subject is seeing every condition multiple times. Now, for the by subject aggregated data, the correct t-test that I would do is this one here, this command that I've run here. I've got raw reading time as a function of condition in the aggregated by subject data, and I get the t statistic and it turns out to be significant, blah blah blah. But the linear model that I had fit on the untransformed data, okay, so right now I'm ignoring the log transform part of the story. I'm not talking about the original model, linear model that I had fit, where I had treatment contrast coding with objects gap coded as the 0 value, coded as 0, and subject gaps coded as 1, right? And so in that original model, when I had fit the model, if you print out the output of this model and you look at the statistical test that is done on the slope, right? So remember that our null hypothesis test was that beta 1 is 0, right? That was the null hypothesis test that the linear model always does. what we discovered to our shock is that the linear model's t-value does not match the t-value of the paired t-test. Why is that? Right? Why do these t-values differ? Well, this is because the linear model is actually doing an unpaired t-test. It's not doing a paired t-test. We are doing a paired t-test here, right? Because this is repeated measures data. The linear model is not doing the unpaired t-test. Okay, so if we had done an unpaired t-test, right? So this is an incorrect test, okay, because it's a repeated measures data set. If I had done an unpaired t-test, I would get exactly the same t-value as from the linear model, right? That's what you're seeing here now. Of course, the sign is different. The sign is different. Why? Because of the way that the difference in means is being calculated. If you calculate the subject mean minus the object mean, you will get a negative difference in means. If you calculate object mean minus subject mean, you'll get a positive difference of means, right? So this is arising from the contrast coding in the two conditions that we have set up here. So don't be confused by the difference in the sign. What's important is that the absolute value of these t-scores is exactly identical, and what this shows is that the linear model is actually the unpaired t-test. Okay. Now, what is the equivalent of the paired t-test in the linear modeling framework? The equivalent is the linear mixed model. So instead of LM, we are going to use this Elmer function, right? And the syntax will be the same as before, raw RT as a function of condition, okay? But in addition, I'm going to add this one term here, which I'm going to explain later, which actually takes into account that I have repeated measurements on subjects, okay? So once I do that, I get exactly the same t-value that I got with the paired t-test. Remember, it was 3.1. It was 3.1, right? The sign is different, but that's not really important because that's just the difference between the means. If you have the right contrast coding set up, the right baseline, you will get the difference in means being plus, the t-value will be plus 3.1, okay? So the point here is that the linear model corresponds to the unpaired t-test. The linear mixed model corresponds to the paired t-test, okay, in the particular situation that I'm discussing here, okay? Okay. The next point I want to discuss is that what happens when your predictor is not a categorical variable like object and subject relative clauses, right? So I had just binary variables that I had here. Suppose you have a continuous predictor, right? Like you can have the height of a person should be able to predict the weight of a person, right? The taller you are, the higher your weight might be. Okay, so that kind of data set is interesting to think about. And I have a nice data set here that we can use as an example. We have some real data from this published paper, which shows you the teaching evaluations on some scale for teachers in a university as a function of their perceived beauty level, right? So what they did, I think if I remember correctly, they divided up the class into two, and half the class rated the beauty levels of the instructors in their teaching program, and the other half rated their teaching evaluation or something like that, right? So basically for every instructor I have a beauty level, right, as a numerical value, and the teaching evaluation. And the expectation was, or maybe they had some theory, I don't really remember, but the idea was that the more good looking you are, or perceived to be good looking you are, the better your teaching ability. Okay, I mean, if you look at me, you obviously know that has to be false because I'm such a great teacher and I look so terrible. So obviously this claim has to be false, but let's just see what the data say. So basically what we have is the teaching evaluations in one column. That's the evaluations, and we've got the beauty values, so to speak, in the other column, right? So the beauty values are actually centered. That means when a beauty value is set at 0, that means that person has an average beauty level. Okay, so that's what it means to have centered beauty values. Okay, so basically what's going to happen now is that we're going to fit a linear model, right? We're going to look at the effect of beauty on evaluation. All right, so one basic model that we can fit is we can just fit a model where we have the evaluation score as the dependent variable and we just have the intercept as the predictor. That's a possible model to fit, right? So here what we're going to be having is that we'll have the evaluation on as a dependent variable and we will just have the intercept with some random variability around it. That means that the intercept will be just telling us what the mean evaluation will be of the teachers, right? That's what the intercept will give us now. So if I look at the mean evaluation of the teachers, it's 3.99. If I fit such a model, that's what I've done. Let's see here, right? What I get as an estimate for beta 0 is the mean evaluation of the teachers, right? So that's one model that I could fit with this kind of continuous measures, right? All right, so now I can actually add the continuous predictor, the centered beauty levels as a predictor. And now what I'm going to be doing is that I'm going to be estimating two parameters, beta 0 and beta 1. Okay, the beta 0 will be telling me the average evaluation score when the beauty level is 0. That means when the beauty level is the average value. Remember that the beauty level is centered such that the value 0 represents average beauty levels. So the intercept now will tell me the predicted evaluation score when you have an average beauty level as an instructor. Okay, so that's what this intercept is telling me now. And notice that the intercept is different from what we had earlier. That 3.99 was the grand mean intercept over all the data of the evaluation scores. Okay, so now we've got the predicted evaluation score for average beauty levels, and the slope is now telling you, this beta 1 parameter estimate is telling you the additional increase in teaching evaluation scores as you increase the beauty level by 1 unit. What that means is that if the model predicts that if your beauty level is 1 unit higher than average, then your teaching evaluation should go up by 0.133. Okay. All right. And so basically what we're seeing here is the intercept and slope are now telling us the relationship between beauty and evaluation. The slope, in fact, is telling us all this, and the statistical test is being carried out here. The null hypothesis test being carried out is that my cat is wanting to go out on the balcony. The null hypothesis test that we want to carry out here is that the slope, the effect of beauty is 0. This is the null hypothesis, right? And so what we are really doing here is that we're calculating literally 0.133 minus 0 divided by the standard error, which is 0.032. I see the standard error here. This gives me the observed t value, which is 4.133, and I know from all the study that we did in the previous lectures that 4.133 allows me to reject the null hypothesis that beauty has no effect on evaluation, right? So there we see a strong, significant effect of beauty on evaluation. Obviously, I don't believe that result, but and in fact, if you look at this data as an exercise, what you should do is just plot the beauty and evaluation data. What you will see is that there's a lot of noisiness in the data, and this model is looking statistically significant for sure. I mean, the model output is showing you statistical significance, but if you look at the noisiness in the data, it's very hard to believe that this is a meaningful result. Okay, so in other words, another way to say this is that these data are probably very variable and noisy, and you have a type M error situation. So this 0.133 estimate, I'm willing to bet, is a severe overestimate, right? If you had data from millions of teachers, you would get probably a much smaller estimate and quite different results. Okay. So we know now how to fit simple linear models with +-1 coding or 0-1 coding of the predictors, right, with a simple pairwise comparison, and we know how to fit simple linear models with a continuous predictor. I think this is a very good start, and this prepares us for fitting more sophisticated models and fitting models with more variables and more predictor variables in them, right? So the more complicated cases. All right. So let's see.